All right, let's dive into one of the oldest, but honestly, one of the most powerful tools in all of machine learning. Think of it like a detective. It's a predictor, and it's really the bedrock for so much of modern AI. Today, we're going to unmask the simple but absolute genius of linear regression. Okay, so to get started, I want to tell you a story. And this story doesn't begin in a modern computer lab, but way out in the cosmos, more than 200 years ago. And no, this isn't science fiction. This is the actual real-world origin story of our very first predictive algorithm. Right, so let's set the stage. We're talking about a prediction made 2 centuries ago that, and this is no exaggeration, completely changed our ability to see the future. So picture this, it's 1801. Astronomers are ecstatic because they've just discovered the very first asteroid. They called it Ceres. But after just a few weeks of watching it, poof, it disappears behind the glare of the sun. They had no idea where it would pop back out months later. I mean, the whole astronomical community was in a total panic. But then this 24-year-old mathematical genius, a guy named Carl Friedrich Gauss, steps in. He uses this totally revolutionary technique to predict its exact path. And sure enough, when December rolled around, they pointed their telescopes exactly where he said to, and bam, there it was. Now, what's so cool about this is how he pulled it off. He used a brand new technique that he'd come up with himself called the method of least squares. And you need to remember that name, because that method, it's the mathematical engine that powers linear regression today. What his prediction proved was something absolutely monumental. That even with just a handful of messy, imperfect data points, you could actually find the true line of nature. You could find the signal hiding in all the noise. So how does this mathematical detective actually do its job? Well, it all boils down to one simple, elegant goal: finding the line of best fit. We're talking about that one single line that best cuts through a whole cloud of messy, real-world data. Okay, let's take a super simple example. Imagine we're plotting a person's height against their shoe size. You and I, we can just look at this and see a general trend, right? I mean, we could probably sketch a dozen different lines that look about right. But that's the thing. Machine learning can't just eyeball it. It needs a precise, mathematical way to find the one single optimal line. So to find the best line, first we have to figure out a way to measure how bad any given line is. And the way we do that is by calculating the error for every single data point. In the biz, we call this error a residual. It's really simple. It's just the vertical distance between a real data point and where our line predicts that point should be. And this brings us right back to Gauss's genius move, the method of least squares. It's a simple process. First, you measure that residual for every single point. Then, and this is the really clever bit, you square each one. Now, why square them? Well, it does two really important things. One, it gets rid of any negative numbers, making all the errors positive. And two, it heavily penalizes the bigger errors. Think about it. An error of 4 becomes 16, while an error of 2 only becomes 4. So points that are way off the line get a much bigger penalty. Finally, you just add up all those squared errors to get a single total error score. And the goal? The whole game is to find the one line that makes that total sum as tiny as possible. So let's say we just draw a random line through the data, one that's clearly not a great fit. Its residuals, those little error lines, are going to be pretty big. After we square them and add them all up, we might get a total error score of, say, 31.71. You can think of that number as our badness score. A higher number means, well, it's a bad fit. But the best fit line, well, that's the line that makes that score as low as it can possibly go. The algorithm is smart. It systematically adjusts the angle and position of the line, almost like it's hunting for that sweet spot with the absolute lowest error. And in this case, it finds a line where the sum of the squared errors is way down at 14.05. And that is our winner. That's our line of least squares. And all of this brings us back to that famous equation you probably remember from school, y equals mx plus b. The entire learning process in linear regression is just about the machine finding the perfect values for m, the slope of the line, and b, where the line hits the y-axis. So how does it actually find them? Well, if you want to peek under the hood, it uses calculus. It basically creates a big equation for that total error score, and then finds the exact point at the very bottom of the curve where the error is at its absolute minimum. That is the learning in machine learning. Okay, but this brings up a kind of weird question about the name itself. If this is all about predicting things forward, Why on earth is it called regression, which literally means to go backward? Well, the name actually comes from a really surprising place. It has nothing to do with finding asteroids or pure math. It comes from a 19th century study of, believe it or not, garden peas. Yeah, the guy we have to thank for the name was Sir Francis Galton. He was studying heredity, and he noticed this really peculiar pattern in the sweet pea plants he was growing.
Here's what he found. The children of extreme parents tended to be, well, less extreme themselves. So when he planted seeds from giant parent plants, their offspring were definitely tall, but they were consistently a little bit shorter than their super tall parents. And on the flip side, seeds from tiny little plants grew into offspring that were short, but actually taller than their tiny parents. It's like everything was being pulled back toward the middle. He called this phenomenon regression toward the mean because the next generation always seemed to move back or regress toward the average. And for whatever reason, the name just stuck.
But look, this 200-year-old idea isn't just some historical curiosity about peas and planets. It has absolutely changed the modern world. Let's talk about how it sparked what's known as the Moneyball revolution. So, if you've ever seen the movie Moneyball, you've actually seen a fantastic example of linear regression in action. The whole story is about the Oakland A's baseball team. They didn't have the money for superstar players, so they had to get smart. They turned to data. They used regression and found out that the traditional stats everyone cared about, like home runs, were actually kind of overrated. The real key, the single strongest predictor of winning games, was something much simpler, a player's ability to just get on base. And that simple line of best fit let a team with very little money completely outsmart the richest teams in the league. And here's the crucial takeaway. This algorithm is working quietly behind the scenes everywhere. You want to predict a house price based on its square footage and number of bedrooms? Yep, that's linear regression. You want to figure out how much your sales will go up if you spend more on ads? That's linear regression too. Hospitals predicting how long a patient will stay to manage their beds, farmers predicting how big their crop yield will be. All of these problems are solved by finding that simple line of best fit. So you might be thinking, okay, this is all cool history, but why does it matter to me, someone getting started in machine learning today? I mean, why would we begin with an algorithm that's 200 years old? Well, because linear regression is absolutely foundational for a few key reasons. First, it's simple. It's easy to understand, easy to implement. Second, it's incredibly fast. It can chew through massive data sets in no time. Third, and this one is so important, it's interpretable. That means you can actually look at the model and understand exactly how each input affects the final prediction. And all of that makes it the starting point. Honestly, when you're faced with a new prediction problem, linear regression should almost always be the very first tool you pull out of your toolbox. You know, from finding lost asteroids to completely changing professional sports, this humble little algorithm is such a powerful reminder that sometimes the most revolutionary ideas are the ones that just draw the clearest, simplest line from point A to point B. So I'll leave you with a final thought. What's a trend in your own life or in your work that could be predicted by a simple line?